In this lecture, we'll look at the possibility of life on nearby regions to the Earth, in particular the moons of giant planets. But first, a postscript on the idea of extremophiles. I said that almost all extremophiles are microbial, but some creatures that can withstand extreme environments are not microbial. They're creatures that look like animals. Meet the incredible tardigrade. This creature you're looking at is no larger than the head of a pin, so we're looking at a micrograph, extremely magnified. But in addition to extreme temperature, pressure, and dehydrated states, tardigrades have survived after 10 days of exposure to the vacuum of space. Tardigrades give us at least one version of biological life that can withstand the harshness of space. This makes the concept of life living in the comparatively warm, wet, and temperate oceans of moons in our solar system less difficult to imagine. Tardigrades are genuine life forms with internal organs that can go into an interesting state called cryptobiosis. To handle situations where the water evaporates or is gone for long periods of time, they essentially dehydrate to 1% of the normal water content and curl up into a tight ball called a ton. These tons have been found in the fur of animals, so tardigrades use this situation to even travel and spread through their environments. And then when rain happens, in a place where rain doesn't happen very often, they can reanimate and go about their lives. Hitchhiking into space on a spacecraft we don't imagine happens very often. Really, microbial life can probably not survive this. A separate area of research, in fact, involves how long microbes can survive inside space rocks. A hypothetical experiment is that in a meteor impact on the early Earth microbes could be ejected into space inside rock, and the question becomes, could they survive this process, and could they travel to other astronomical objects? Evidence suggests that deep inside a rock, more than 1 inch deep inside rock to protect from solar radiation and cosmic rays, microbes can survive for hundreds of thousands of years and perhaps millions of years. So in addition to living in inhospitable environments, microbial life could potentially travel through space, especially between the objects in a solar system. This idea is called panspermia. Let's drop back to the big picture of astrobiology and just ask why it is that astrobiologists are so confident that biology may be common in the universe, especially given the fact that as we speak, life is only known in one location in the universe. We've seen the various pieces of this. We've seen the fact that life formed very early in the history of the Earth when conditions were very inhospitable. We've seen that organic molecules and the ingredients and building blocks of life can form easily and naturally, even simulated in the lab. We've seen that the ingredients for life at the level of carbon, nitrogen, and oxygen, and water vapor exist elsewhere in space, even in distant galaxies. And so chemistry is universal. We've seen that life on Earth can sustain a wide range of activity under extreme physical conditions. And from the study of exoplanets, we've seen that the planet and moon habitable locations are widespread and very large in number in the Milky Way galaxy and elsewhere. So we're faced with the plausible speculation of life on other worlds. This dialogue, this questioning and this speculation is actually thousands of years old. We can read from Epicurus' letter to Herodotus, where he says, "There's an infinite number of worlds similar to ours, and an infinite number of different worlds. One must agree that in all these worlds, without any exception, there are animals, plants, and all the living things we observe." That's an extraordinary statement occurring over a millennium before the Copernican revolution. We recognize that it's a philosopher with no evidence to back up his supposition, but he's arguing the Copernican principle that there's nothing special about the Earth, including its situation in space and the presence of biology on the planet, even at the time where biology is not truly understood. However, among these early thinkers, Epicurus and other cousins of his in their thinking did not persist. The dominant strain of thought was defined by Aristotle, perhaps the most powerful and influential philosopher in history. Aristotle pushed the geocentric cosmology, and that mostly squashed any discussion of the plurality of worlds until the Copernican revolution. So from a philosophy of a geocentric cosmology where the Earth is the center of the universe and special, it becomes reasonable to squash the idea of other worlds comparable to the Earth and other forms of life. Aristotle would not have been a supporter of modern astrobiology. Is the pale blue dot special? Remember, that was the term given by Carl Sagan based on this image from the Voyager spacecraft of the Earth suspended like a gossamer strand of light against the diffraction spikes of one of the cameras in the instrument. The Earth backlit is almost certainly not the unique host for biology in the universe, but we need the evidence to back that up. So what do we find looking through the solar system based on information from recent space missions? With Titan, a large moon of Saturn, we find an interesting cousin of the Earth. Not as large as the Earth, for sure, but a moon with a nitrogen atmosphere thicker than the Earth's, with active geology, with weathering, with bodies of liquid on its surface. If we look at these pictures of dendritic channels, of liquid flow, of clouds, of lakes, it's incredibly Earth-like. And yet this is nothing like the Earth. This is so far from the Earth, very far from the sun, that the temperature is far below the freezing point of water. The lakes and erosion features are almost certainly a mixture of ethane and methane, probably mixed with a very small amount of water and ammonia. However, they could potentially be sites for complex hydrocarbon biochemistry. Lab experiments to simulate this are very difficult to do, and they're still ongoing. But the mere speculation that there could be hydrogen biochemistry based on very different chemical basis than the Earth is fascinating and worth exploring. Here we see an amazing picture taken by NASA, taken by the Cassini mission, of sunlight glinting off a lake on Titan, the first image of reflection off a liquid on another world. But this liquid is ethane and methane, not water. How is liquid even of ethane and methane kept liquid so far from the sun? It's because there's hydrovolcanism. Titan is a big enough moon that its rocky material generates interior heat, and that interior heat percolates through the lakes of ethane and methane. And there's a fair amount of heat deposition and even volcanism at the base of those lakes. Another eerie similarity with the early Earth. Titan may be the most compelling target for life, especially life unlike that on the Earth, life 2.0, given its nitrogen-rich atmosphere and the abundance of surface liquid and the probability that there are complex chemical reactions in those liquids. Unfortunately, it's far from the Earth. Cassini launched the Huygens probe, which landed on the surface of Titan, sent back some pictures, and essentially half an hour of data before its battery died. Astronomers and planetary scientists would love to go back to Titan, and we have the technologies to send dirigibles around it, sampling the liquid in its oceans and lakes over a period of years, and doing experiments to detect potential forms of life. The technology and the mission plans exist. NASA doesn't have the money for it, and it will take 10 or 15 years to get there. But this is a compelling place to look for life beyond the Earth. Even more similar to the Earth are the water worlds in the solar system, some of which are poorly understood. The most well understood is Jupiter's moon Europa, one of the Galilean moons of Jupiter. It's the closest thing in the solar system to a water world like the Earth. In fact, it has water entirely across its surface, all covered with an icy cap. It's a large enough moon to have significant radioactive heating from the core. It's also close to a giant planet on an elliptical orbit, so it has an additional component of tidal heating. So once again, although it's 5 times further from the sun than the Earth is, there's localized heating that could be the basis for biology. And we're talking about water, which is the other ingredient for biology. So this water's oceans may be tepid or warm, especially in some subterranean regions near volcanoes. The icy crust covers an ocean that is over the entire surface of the planet, so we can't see the ocean anywhere. In fact, ice facing a vacuum like this in intense cold is as hard as granite. So it will be quite a challenge to design a mission to explore this moon in detail. This is a cross-section of what we believe Europa looks like. It's based on models. We don't actually know, but the speculation is that a few kilometers of icy crust overlie an ocean tens of kilometers deep, over the entire surface. Europa is another compelling target for planetary missions. NASA and the Europeans have traded off ideas for a Europa Clipper, or a probe that would orbit Europa. The most ambitious and aggressive idea, of course, would be a lander. And the most avant-garde idea, dating back from the 1970s, would be a lander with a nuclear power plant that could melt through the ice slowly and release a hydrobot to search for life in the European Ocean. That mission has existed as a concept for almost 50 years and is unfunded. But it's likely that there will be a mission sent to Europa, which will stare in detail at it and possibly send a probe to splash off ice from the surface and then sniff that ice with chemical and spectroscopic probes as we pass around the surface, the way it was done with Enceladus some years ago. So Europa is another compelling target to look for life beyond the Earth. Here's the hydrobot in a model from a NASA mission proposal dating back to the 1970s. So these missions are not funded. And for all of these outer solar system missions, the timescales are 10, 15, or 20 years, and the price tags are several $billion. NASA's budget is $18.5 billion. It's a large amount of money, but the free energy, so to speak, in NASA's budget is only about $500 million a year. And there's a lot of new things NASA wants to do, so funding any of these missions, given the other priorities, is always difficult. A third target of compelling interest, and the interest is more recently based, is Enceladus. This small moon, about the size of Rhode Island, was a complete surprise when icy jets were found emerging from its surface, seen here in silhouette. Enceladus is so small it has no atmosphere. It's in a very elliptical orbit of Saturn and quite close to it, so it has tidal heating and therefore an internal heating source, even though it doesn't have much rocky material. So NASA's Cassini mission 10 years ago observed plumes of material escaping from this little moon. And then with its spectrometer, it was able to fly through those plumes and measure the composition chemically of those tiny ice particles. There was carbon dioxide, there were methane, and various other hydrocarbons. The plume supplies ice particles to one of Saturn's nearby rings. Some of the ice particles are salty, which indicate they probably originate in a salty ocean deep below the icy crust. The plumes are coming through fractures in the surface caused by probably the tidal heating. And this is a place where the ice can escape. Of course, in the low temperature and vacuum of space, the water immediately goes into tiny ice particles which shoot off into space. So we would love to learn more about Enceladus, and the speculation of what might be happening in these subsurface oceans is fascinating. This time-lapse from the Cassini mission, which orbited Enceladus and took pictures of the icy geysers, shows the incredible ejection of particles of water, frozen, into space. We'll watch it loop a couple of times so you can get a sense of the extraordinary situation where this tiny little moon, smaller than the state of Rhode Island, somewhere in it has liquid water, and that liquid water is being ejected into space. This tiny moon has all the ingredients for life in our solar system. Could Enceladus host life? And if a tiny little moon of a giant planet could host life, how many possible other places might there be life in the solar system and beyond? Remember that models of even more distant moons around Uranus and Neptune suggest that a handful of them, perhaps as many as 6 or 8, also have liquid water, kept liquid by geological heating, tidal heating, and under a rocky and icy cap. So Enceladus is not alone as a small moon that might host biology. Until we can get next generation missions, which are, as I've said, long time scale and expensive, we can only imagine and visualize life on these tantalizingly nearby worlds. Astronomers have been speculating about the existence of life beyond the Earth in the universe for centuries. Going back to the ancient Greeks and Romans, there was the idea that the Earth was not special and that life forms might exist elsewhere. Aristotle's geocentric idea that the Earth was the center of everything and special essentially squashed the basis of astrobiology for a long time. But now we know that life can exist in a range of conditions, and we can identify even nearby worlds where it's possible that variants of our biology might exist. One is Titan, with its thick nitrogen atmosphere and bodies of ethane-methane liquid. Another is Europa, a water world orbiting Jupiter, where there's water and also some internal heating from tidal effects and from radioactive decay. And then, most surprising of all, the tiny moon Enceladus, similar to another half dozen or so moons in the outer solar system, where there's liquid water under a rocky and icy cap. If there are that many places in one solar system with all the ingredients for life, how many might there be elsewhere in the universe?